Welcome to today's lesson on potential difference, energy and charge. Please put the data in here very quickly. Where are we? Well, we're now on to this lesson here. E equals QV or equals VQ. And it's another calculation based lesson. So it's a formula that enables us to work out how much electrical energy is being transferred when we move charge. I will know and understand what makes electrons move around a circuit. I will understand why high voltages can cause increased currents, and I will be able to solve equations using the formula E equals VQ. Energy equals potential difference times charge. So to get started, to get warmed up, have a go at these two formula-based questions here and then have a think about this one. I will reveal the answers. Hit pause and I will reveal the answers in a minute. Okay, a bulb has 60 coulombs of charge passed through in 2 minutes. What was the average current in the bulb? Well, the formula here is going to be Q equals I times T. Let's put the numbers in. Well, let's rearrange it. So I equals Q over T. Bring the T down here. If you think, imagine the triangle with the Q on the top. Put the numbers in. 6 divided by charge is 60 coulombs, that's wrong. 60 coulombs divided by 120, which is 0.5 amps. If the bulb above had 6 volts across it, what was the power being dissipated in the bulb? Right, so we had 2 minutes. The bulb, so we're going to use P equals IV here. P equals IV, 0.5 times 6, that's the current times voltage from here, which means 3 watts. What is the role of the potential difference in the circuit? Well, there's no specific answer here. This is leading into the next part of the lesson. But I suppose the role of the potential difference, you could think of it as it's really driving the electrons or pushing the electrons around the circuit. We're going to explain in the next stage of the lesson exactly what it means, potential difference. So let's move on. Okay. A little bit of explaining going on here. Hopefully you've seen this page before. Electrons are charged particles, and each one of them have a very tiny charge or attractiveness of minus 1.6 times 10 to the minus 19 coulombs. So that's a very tiny amount. We'd have to move that decimal point down 19 times there. It'd be 0.000000000000016 coulombs. If we take enough electrons together then, so this is what I'm trying to represent in this graphic here, and we could think of 1 coulomb of charge, but you'd need lots and lots and lots of electrons just to get 1 negative coulomb of charge. A coulomb is a relatively large amount of charge compared to an electron. And what does that mean? So 1 amp means 1 coulomb per second. So we're talking about lots and lots and lots and lots of electrons flowing through a point in 1 second. Maybe have a go at doing this one. I'll just pause it here. How many electrons in 1 coulomb? How would you go about doing that? Take a minute and see if you can calculate an answer. Okay, here we go. Well, the amount of coulombs in this is a calculation we need to do. There's no formula for it. How many electrons, so that's a charge of 1 electron, would fit into 1 coulomb? So I take 1 coulomb and I divide it by the charge of an electron. Do it on the calculator. And you'd end up with this number, 6.25 times 10 to the 18. Now this is the opposite really of times 10 to the minus 19, that this is a very large number, so you need to move this decimal place down 18 times. So we're really looking at 6 million electrons approximately. So 6 times a million times a million times a million electrons would just to make 1 coulomb. Okay, let's try and explain really now what we mean by potential difference. I'm going to start this by doing what we call a little thought experiment. Imagine you've got a ball of positive charge here, and you've got a ball of negative charge, and they are free to move along this conductor. They can either go this way or that way. The positive can either go this way or that. If I left them and they could move either way, they had a big positive plate over this side, they have a big negative plate over this side, which way would they tend to go? Give yourself some thinking time here, and then I'll just explain what they would do. Okay. In effect, the positive charge would actually want to go that way. The positive charge would want to go that way because the positive charge would be attracted to the negative. The negative would want to do the opposite. So we'd actually end up with a situation probably a bit like this. Positive going that way. Now, that's really the arrows I'd like you to draw on the diagram. But let's just stop here and think. If someone grabbed hold of this, like I'm going to grab hold of this now, and I drag this across here, well, I could do that, but I would have to apply energy, because as soon as I let go of it, it would spring back a bit. And if I applied energy, I could drag it over here. But as soon as I let go of it, it would want to go back here. So you can move charges against their will through this is in effect an electric field. You can move charges against their will, but they'll always go back. And the amount of energy, the more positive this plate, the more energy is required to move my positive charge over there. The more positive charge I have on here, the more energy I'm going to need to apply to move it across there. To measure how difficult it is to move charge, we use an expression that you've already come across before. It's called potential difference. So let's just put those back to where they are. So that's what your diagram in your book should look like. Rewind this section if you want to just check what I was saying there. So, put in your book, why did you draw the arrows the way you did? Well, fundamentally, because charges always are attracted to the opposite. The positive charge gets attracted to the negative plate, and the negative charge gets attracted to the positive plate. Fill that in there, please. Okay. So this is a definition that we use at A level. So it's not necessarily required here, but really, what is a volt? What is potential difference? What's 1 volt? Well, really what we're doing when we're measuring voltage, we're measuring the amount of energy per unit charge between 2 points. 1 volt is actually 1 joule per coulomb. If you move 1 coulomb through 1 volt, then that takes 1 joule of energy. Or another way of saying it, if you apply 1 joule of energy to 1 coulomb, then the difference between those 2 points is 1 volt. Volts, the SI unit of volt potential difference is 1 volt, and that's actually the same as 1 joule per coulomb. We don't normally write that one. It's a bit like the way amps is equal to 1 coulomb per second. So let's have a look at a formula here. We've got E equals Q V, or E equals VQ, would be the same. We've got 3 formulas that fall out of this. E equals VQ, cover up V, and we will find, well, let's do it, cover up V, we end up V equals E over Q, and if we cover up Q, we'll end up with E over V. There's the 3 formulas. just another one more way we can look at this. Let's have a look at, here's a circuit. It's got a voltmeter across the bulb here, and we're showing the electric current is flowing around this way. So 1 amp. What does that mean to have 4 volts? Well, in this diagram, you want to think of these coulombs moving around. These are different times. So here's a coulomb. It's coming along, it's approaching the bulb. It's got 4 joules per coulomb, 4 joules per coulomb, 4 joules per coulomb. And it gets to the bulb. What's it giving to the bulb? Well, it's not giving any of its charge to the bulb. It's just giving away its energy. And when it gets onto the other side of the bulb, can we see what's happened to the coulomb? Well, the coulomb's exactly the same. The electrons, in effect, are all exactly the same. They've just lost their energy. What's the energy difference here? What's the energy difference between the start and the end? It's 4 joules per coulomb here, 0 joules per coulomb here. So it's 4 joules per coulomb. It's what we call a potential difference. 4 joules per coulomb. 4 volts. How much energy is required to move 10 coulombs of charge through 6 volts? Let's just write this down here. Nice. E equals VQ. E equals VQ. Okay. How much energy is required to move 10 coulombs? That's charge, Q, and that's the potential difference, V. So E equals VQ. 6 times 10, which is 60 joules. That's easy. It takes 2000 joules of charge to move a certain amount of charge through 10 volts. So I've got V, I've got E, energy, and how much charge? How much charge? Well, E equals V, Q. So Q equals E over V, which is 2000 divided by 10, which is 200 coulombs. If you just think what a volt is, 1 volt equals 1 joule per coulomb. So 10 volts means every coulomb has 10 joules of energy. So it'd be 200. That would give us 2000. It just makes sense. The energy required to move 100 coulombs of charge is 2000. What was the potential difference? So E equals VQ. We always write that down. This is my Q and this is my E. V equals E over Q, which is 2000 divided by, in this case, 100, which is 20 volts. 20 joules per coulomb. That just means the same thing. 60 coulombs of charge flows through a resistor that has 3 volts across it. How much work is done by the cell pushing the electrons through the bulb? So we've got Q and V. How much work is done? Well, remember, work done equals energy transferred. Well, what's transferring the energy here? Electrons. This is a transfer of energy via an electrical circuit. So we can say E equals VQ, 3 times 60. This is the work done. This energy here is the work done, which is 180 joules. Right, this one looks a little bit more tricky. There's V. A 1.5 volt bulb has a 1 amp flowing through it for 20 seconds. How much charge flows through the bulb? Okay, so they're asking for Q here. How much charge? How much work was done by the cell to push electrons through the bulb? How much energy was converted from electrical energy to other forms such as light and heat? So the first one is how much charge flows through the bulb. So we've got Q and we've got V, but we haven't got E, so we can't do E equals VQ. But we have got Q here, but we've got I and T. So we're going to start off using Q equals IT. What's the current? 1 amp times 20. 1 amp, 1 coulomb per second times 20 seconds. We've moved 20 coulombs through that bulb. Now we've got Q and we've got V and we've asked how much work was done. Well, this is just the same as above. Who's doing the work? We're transferring the energy. So E equals VQ. V is a 1.5 volt bulb. In the 20 seconds we moved 20 coulombs. So 1.5 times 20 is 30 joules. How much work was done? So how much work was done without a cell? How much? That's this answer. How much energy was converted from electrical energy to other forms, such as light and heat? Well, this is bringing back this idea about energy transfer. Work done is energy transfer. In a circuit like this, you remember, the cell, the electrons, do the positive and negative, and as you remember, the electrons actually go that way, but the actual current goes this way. Now, if you remember all the way back to energy, first of all, we said it talked about work done equals energy transferred. You also remember that electrical was not an energy store. It was an energy transfer. In this case, it's transferring chemical energy into light and sound. Chemical energy from the cell into light and sound. So the final part is light and sound, light and heat. Light and heat for a bulb, clearly. Light and heat energy must be equal to the energy of the electrons, because that's the only energy that's coming out. So that's going to be 30 joules as well.